Okay, let's continue our conversation about polynomials here. Let's get the screen bigger. Here we go. All right, we already briefly in a previous video talked about end behavior and how the degree of the polynomial determines whether it starts and ends the same, okay? And whether or not the leading term, if it's negative, it'll end down, and if it's positive, it'll end up. So in these boxes here, it's kind of recapping that, that information. So here, leading coefficient is positive, and the degree is an even number. So x to the power of 2, x to the power of 4, x to the power of 6, even. This one over here, the next one over, leading coefficient is positive, but it's an odd degree. We will see that it still ends going up, but it starts and ends in opposite directions. When we're asked about end behavior, these are the things we've had conversations about. Now, if our leading coefficient is negative in these two cases, it has an end to the right behavior of down. And if it's even, it starts and ends the same. And if it's odd, it starts and ends opposite. Okay. Now, as we progress to polynomials, we're going to have increasing and decreasing come to play. So I like to tell students that if you're just tracing the graph from left to right and your pencil is moving down, now you're decreasing. If you're tracing left to right and your pencil is moving up, you're increasing. Pencil's moving down, decreasing. Pencil's moving up, increasing, right? That's probably review for you. But now, this point right here, this point right here, and this point right here obviously are all turning points. Not only are they turning points, but they are local maxima or minima, okay? Now I say local because this one has an arrow up, this has an arrow up. So this is just a local max. It's the max in the little neighborhood. It's not the max over the entire graph. This is a local min because it's not the lowest overall. It's just the lowest in the neighborhood. This is a local min because it is the lowest in the neighborhood, but it is also the maximum minimum because it's weird to say that. Actually, let's rewind that. Let's not use the word maximum minimum. Let's use the word global or absolute. Some books use the word global. Some books use the word absolute, but because it's the lowest of the entire polynomial. So it is both technically a local and an absolute. I believe for homework purposes, they want you to just clarify the most encompassing definition for that one, and I would say that's absolute there. Okay, we talked about in a previous video that if your degree is n, then the turning points are at most one less. Okay, we've done that as well. Okay, let's move on. Find the maximum number of turning points for each polynomial. Well, it might be out of order, but this polynomial has this for the leading term. So the degree is 5. So max turns is 4. Next one, it's not in like standard form where it's all multiplied out, but we can still envision which would be the largest term if we did multiply it out. So let's see, the largest for this group is 2x squared. If this got multiplied out, the largest term would be an x squared, and there's a negative out front, and this is all multiplication. So our leading term is going to be a negative 2x to the 4th when we're all done. So that means my degree is 4. So the maximum number of turns, this is number of turns, 3. Okay, all right, moving on. Let's talk about sketching polynomial functions. Yes, we have some steps here. I'm going to say we'll deal with some symmetry later. We don't have to prove symmetry at this point in the course. So you can take a pause on the checking for symmetry algebraically. However, it's nice to notice symmetry visually, right? So we could do, there's symmetry that's a rotation around the origin. That would look something like this. 180-degree rotational symmetry. Whoops, I forgot this first one. We have symmetry about the y-axis, and that would look something like this, right? So those are the two types of symmetry that we do test for in this course, but for the purposes of sketching polynomials, we won't have to algebraically. We'll just look at the graph and determine those for now. Okay, so we have a polynomial here in example 8. We're going to find the x-intercepts. Well, looking at this, I can see that the x-intercepts are going to be when x plus 3 equals 0, and that looks like a double, right? And x minus 5 equals 0. So negative 3, positive 5. This has a multiplicity of 2, and this one has multiplicity of 1. Okay. Now, the overall degree, right? Well, let's see if I did that. Multiplicities. Okay, I found the multiplicities to determine the behavior and the x-intercepts. Got that? Determine the end behavior. Okay, let's look at the leading term. So this was kind of 1 and 3. Let's look at 4, end behavior. So these are the steps. Let's see, end behavior. So leading term, if I multiplied this part out, I would get an x squared. This has a leading term of just x. Those are multiplied, and there's a negative 2 in the front. So negative 2x cubed is the leading term. I like this because I can see that the total multiplicities have to add up to the degree, right? So obviously I have a degree 3. And end behavior, as x goes to the right, the function f of x goes down. Why? Because as x gets bigger and bigger and bigger, it'll be positive, but there's a negative in front. Okay? All right. And then they're going to start and end in opposite directions because it's an odd degree. Okay, so let's go to sketching this. We also know that from the previous video, if it has an even multiplicity, it just touches the graph. If it has an odd multiplicity, it goes through. And by the graph, I mean x-intercept. It touches the x-intercept, and this one goes through, or in other words, it crosses the x-intercept. So let's find those spots. Negative 1, 2, 3 is here. 1, 2, 3, 4, 5 is here. I know that it's going to end down, so it's going to end down this way. It's going to cross here, and it's going to touch here, and I know it's odd, so it's going to end up on the left, okay? All right, so maybe we should look for the y-intercept to have a really good, so we've done 4. We have done 5, so this was 5. Turning points needs to be 2. Okay, and then I am going to find one more point. I should have, let's add points as needed. So if let's plug in and to try to find the y-intercept. If I try to find the y-intercept, f of 0 will equal -2 times 9 times -5. So I get a 90. Oh, that's going to be really steep. All right, so here's 0, 90. All right, graph's going to come up here, come through here. At some point, it has to turn. It doesn't have to turn on this spot, okay? At some point, it turns. We don't know where, but goes through that spot, comes down here, just touches, and goes like that. How many turns do we have? 2 turns. Excellent. All right, moving on. And we can certainly grab our graphing calculator and check it. Maybe we should do that here quick. Let's get our calculator. There it is. Let's see, we have y equals -2 times the quantity x plus 3 to the power of 2 times x minus 5. Graph it. Our graph looks pretty much like that. Let me see if I can get this to fit. Let's do window instead. Y max. There we go. Oh, it went way up there past the 90, didn't it? All right, I like my graph. I think what I have for a sketch is sufficient for what we were doing without more data points. So, all right, I'm going to pause this one here. Pick it up.